Hi, welcome back to educator.com. Today we're going to talk about graphs. A graph is a visual representation of a function or equation. So while perhaps not as precise as numbers and variables, a graph gives us an intuitive feel for how a function or equation works, how it looks. This graph is able to convey a wealth of information in a single picture. Now, just like functions, you've definitely been exposed to graphs by this point. You've seen them in previous math courses, but you might not have fully grasped their meaning. This lesson is going to crystallize our understanding of what a graph is telling us about what a function or an equation that it's representing. It'll tell us what it means exactly. That's what this lesson is here for, to get us all on a same base for graphs so that we can move forward and understand everything that's going to come next. Graphs can tell us a whole bunch of information very quickly. They come up all the time in math. So it's really important. We absolutely have to start off by understanding what a graph represents, because we're going to see them all the time in math and in sciences and in other things. Having a really good understanding of what graphs mean is just going to matter for basically our understanding of a huge amount of other stuff, so we really want to start off on the right foot. All right, let's get on it. Okay, so when we have a graph, it shows how the input affects the output, or how one variable affects the other. But what does that mean, and how should we interpret the pictures we see? So to answer that question, we're going to consider the graphs of f of x equals x plus 1 and the equivalent graph of y equals x plus 1. This graph over here is the same for both of those. Either that function f of x equals x plus 1 or that equation y equals x plus 1. We're going to get that same graph on the right side. Remember, from past math classes, we always associate the horizontal axis with the input independent variable. So our x is the input variable, the independent variable, and the vertical axis gets connected to the output, or the dependent variable, which is normally going to be f of x or y. So over here, the vertical part connects to f of x or y, while the independent input part connects to the x for this function and this equation that we're going to be talking about. One way to think of a graph is as a way to see what happens to various inputs. If I plug in some number for x, where does it go? What happens to this number? The graph lets us see how different inputs are mapped to various inputs. How various inputs are mapped to various outputs. We get to see a whole bunch of inputs getting mapped to a whole bunch of outputs all at the same time. That's what a graph is showing us. So let's interpret the graph of f of x equals x plus 1 with this idea in mind. The reason 2, 3, say 2, 3, right? 2, the horizontal, 3, the vertical portion. The reason 2, 3 is on the line is because if we use x equals 2 as input, then if we plug in 2 into f, if we plug it in for that x, then we'll get 2 plus 1, and 2 plus 1 is 3. So if we plug in 2, it spits out 3 right here. So that's where we're getting this graph from. With this line that we see is all of these possible inputs on this x-axis. Each point on that line shows where the x value directly below it is mapped. So if we look at 7, then it tells us, oh hey, that came out as an 8. If we look at -4, it says, oh hey, that came out as -3. Right? We plug in a value from the x-axis and it comes out on the y-axis. We get to see what does this function do to that input value. And that's how we're looking at a graph. The input goes in from the horizontal and the output comes out on the vertical axis. So it's a really great way of being able to see how the function affects many inputs all at the same time. As opposed to having to look at a table where each one takes up its own entry, we get to see this nice curve or this nice line that explains many pieces of information very quickly, very succinctly. We can take it in a single look. We can also think of it, though, as the location of solutions. This is another way to interpret the graph that's kind of different than that other one. They're connected, but they're also fairly different, and I think in a way that we think about it, it has a real different meaning in our head. The graph of an equation is made up of all the points that make the equation true. So while that's the same thing as input to output, in some ways, we're going to see that we can also say the reason why this point is here, the reason why this point gets to be on our graph is because it works with the equation. It is truth. The points that aren't on our graph, the points that sort of aren't highlighted in the graph, that they're just on our plane, those don't make truth. Those are false points, and so since they would make the equation false, they don't get to be on the graph. Only the points that would make the equation true get to be on the graph. So the graph is all of the truth points, all the points that make our equation actually work. Let's interpret the graph of y equals x plus 1 with this idea in mind. So the reason why 2, 3 is on the graph, so we go 2, 3. The reason why this point here is on the graph is because if we set that into our equation, 2, 3, then if we plug that in, here's the 3 is y. Here's the x is 2. If we set that up as an equation, 3 equals 2 plus 1, yeah, that's actually true. 3 does equal 2 plus 1. So because 3 equals 2 plus 1, it's true. 3 equals 2 plus 1, it gets to be on the graph. 2, 3 gets to be on the graph because the equation that would connect to that, 3 equals 2 plus 1, is a true equation. Every point on the line is a solution to the equation. It's all of the true points, all of the points that would make the equation true. 8 equals 7 plus 1 gives us the point 7, 8. Negative 3 equals negative 4 plus 1 gives us the point negative 4, 3. Oh, whoops, not negative 4, 3, but negative 4, negative 3. Sorry about that typo. And that's what's going on right there. If we were to put on some other point, say let's just consider 0, 10 for a second. We consider the point 0, 10. Well, if we consider 0, 10, if we were to plug that in, we'd get 10 equals 0 plus 1. Wait, that's not true. 0 plus 1 is not equal to 10. 10 does not equal 0 plus 1, so this point here is a false point. It doesn't get to be on our graph, and that's why the graph is just made up of that line. That red line is because those are all the points that actually give us truth. If we went with some point that wasn't on that line, it would actually wind up making our equation false, so it doesn't get to be on the graph. So we can interpret a graph as the place of truth, the location of all the solutions to the equation. This gives us two very different ways to interpret, and they're both totally valid and useful. That said, generally we're going to want to think in terms of the first one. For the most part, the first one's going to be the easier way to think about what a graph is telling us. For functions, it's almost always easiest to think in terms of how inputs are mapped to outputs. For equations, it's not always best, but we can normally use it as well. We can normally use this method for equations as long as they're in that form y equals blah, 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 right? If it's set up with a bunch of y's showing up in multiple places, we can't really use this because we don't have a good way to go from input to immediately showing us what the output has to be. So it has to really be in this form, y equals blah, 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 but that's really what we're used to. When we see something like y equals x squared plus 3x plus 1, it's set up in this form of y equals blah, 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 stuff involving x. But in either case, as long as we're in this y equals blah, 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 or we're just looking at a straight function f of x, in either of these two cases, this interpretation is a great way to think about graphs. We plug in an input, and then we get an output on the vertical. We plug in a horizontal location as the input, and that spits out a vertical location as the output, which gives us an ordered pair, which we can now plot on our plane when all those points put together make a graph. This is a really useful way. It's really easy to grasp. It's very intuitive, and it works very, very well. Still, at other times, it will actually be more useful to think in terms of solutions. What point is a solution? Where is it true? This idea is going to be especially important for certain types of equations that we'll get seen later on, but it's also going to matter for when we want to talk about where two equations or where two functions intersect, where they have the same value at a certain point. So that idea of where is it true, two things being true at the same time, that's an interesting idea and useful for those locations of when we want to talk about intersection or when we want to talk about certain more complex equations that aren't just in the form y equals blah, 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 but where y shows up on both sides or x and y are mixed up together. So sometimes we'll want to use that second form, but for the most part, we want to think in terms of that first way, but the second way we will occasionally use sometimes. So think in terms of that first way. Think in terms of input goes to output, but don't forget about the second way of these are all the places where it is true. These are all the locations of the solutions, because sometimes we'll need to switch gears and think in terms of that because it will make things easier for us to understand at certain later points. All right. Now that we understand what it's about, let's talk about axes. The axes are, just the vertical axis and the horizontal axis, those lines that we are graphing on. The location of a graph can be as important as its shape. The location is set up by its axes. We want to pay attention to these axes. The axes will tell us where the graph is and what scale it has. Often our axes are going to be square. That is to say, the x-axis is the same length as the y-axis. So for example, we might have -10 to +10 on our y-axis and -10 to +10 on our x-axis. This is a pretty common one, and this is square because the x-axis is the same length as the y-axis. So when we look at the picture, it is square, which is sort of an odd idea. But if we made it so that they had different lengths, but we had set them out as the same amount of line, then we would have a sort of squished picture. It wouldn't be the natural picture where we think of width and length as meaning the exact same thing in terms of length. That's a little confusing because we're using the word width and length. I mean width and height meaning the same thing and how long it is. So as long as it's square, the graph isn't distorted from the square perspective we normally expect. However, sometimes it's going to be useful to graph functions on axes that are different from each other, where we're going to want to have like a really big y-axis, really big y-axis, but very small x-axis, where the function grows very quickly. So we want to be able to show all of its ability to grow, but since it does it so fast, we need a short x-axis. So this is another really important reason to pay attention to the axes. You want to know how long they are, what amount of information is being represented in both of them, and also how big it is and where we're located. So you want to have some sense of what the scale is. Are they the same scale on both the x-axis and the y-axis? And just where are we located? Are we located in a weird place? Is it not centered on 0? Those sorts of things. So let's look at a single function. Let's look at f of x equals x plus 1 and see how the many different graphs we can get out of it just by changing the axes. Just by playing with the axes, we can get totally different looking graphs. Here's the standard graph, our -10 to 10, -10 to 10. This top left graph here is basically sort of what our standard graph would be. We are nice and square. The y-axis, the x-axis are the same length. That's what it means to be square. It's from -10 to 10, -10 to 10, sort of numbers that we're used to and expecting. And also the origin is in the center. We've got 0, 0 in the center of the graph. Now let's consider the one below that, so the bottom left. In this one, we've got still square axes because we're going from -2 to, actually they're not, well, they're still square technically. So -2 to 15 and -1 to 16. So -2 to 15 means a length of 17. -1 to 16 means a length of 17. So even though they aren't putting down the exact same numbers, it's still a square because they have the same length total. So -1 to 16, -2 to 15, both a length of 17. So it's still a square graph. So this one here, square. This one here, square as well. So there's no distortion, no squishing in either the horizontal or in the vertical, no squishing of the graph. And the origin, though, is in a totally different place than the center of the graph. The origin is very bottom left corner, right? But it's still giving us the same x plus 1. So looks kind of different in terms of where the axes are, but it's still pretty clearly the same graph, same function making it. Let's look at another one. Well, this one right here is actually not square. Why? Well, we've got totally different lengths here. -10 to 10 and -5 to 5. That means the length of the horizontal is actually double the length of the vertical. The origin is still in the middle, so that's nice. That's something we're used to. But because we have a much shorter length, we have more stuff in the horizontal than we do in the vertical. So that means we have to compress what we're doing in the horizontal. So it's gotten squished left-right, which has caused it to stretch up vertically. So this is not a square axes. These are not square axes right here. Another one that's not square, and hopefully you can read the yellow. Not too easy to read the yellow, but it's just me writing not square here. Once again, from -10 to +2, -20 to something, but -10 to 2, length of 12, and -20 to something greater than 0 means greater than 20. So once again, we've got not square axes. But this time, we've got the vertical axis is longer than the horizontal axis, right? Horizontal axis length of 12, vertical axis length of more than 20, so that means that we have stretched it in the horizontal. As opposed to being squished horizontally, it's been stretched horizontally because now it's got less stuff to have horizontally than vertically. We've squished it vertically because we're trying to cram in more vertical information while not having to cram in as much horizontal information. So it's been squished vertically. So we've got very different things here. Vertical squish has happened in the bottom right one, and in the top one we've got horizontal squish. But it's not because of anything that's happened to the function. The function is x plus 1 for every single one of these graphs. But the squish can be caused based purely on how we set up the axes. So setting up the axes, paying close attention to what the axes are telling us, is really important for us to actually understand what's going on in a function. Unless we understand what the axes are telling us, we won't actually know what this picture means. So make sure you pay attention to axes, otherwise you can have no idea where you are. You have to have a map before you can really make sense of what's going on, and the axes are the map that our graph lives on. All right, one thing you might have noticed by this point is that the graphs in this course, unlike this one to the right, do not have arrows on them. I mean these arrows up here, right? So at some point in the past, you've probably had a teacher who required you to draw arrows on the ends of your graph. And that made sense. They were trying to get across a very specific point to you. They were trying to remind you that the function keeps going on even though we couldn't see it anymore, right? In a way, we can think of the axes as sort of boxing in the function. We don't get to see anything outside of the box of our axes. But in reality, the function doesn't stop at 3, doesn't stop at -3 necessarily. This is just a nice normal parabola. The function would keep going on, right? It would just continue off and off and off, and continue off and off and off and off, right? It doesn't actually stop. So the reason those arrows are there is to remind us, hey, it goes past the edge of our axes. Just because the axes are here doesn't mean it stops. It's going to keep going. So that's what those arrows were for. At this point, though, I think you've probably gotten used to that idea. We're not going to be using arrows at the ends of our graph in this course. The ends of our graphs in this course are just going to stop on our graphs, but that doesn't mean that the function stops. We're going to assume that we're all aware the graph keeps going. It doesn't stop once it hits the edge. It just keeps going, unless we've been very specifically told that the function stops at a certain location. So the graph is only stopping because the edge of the graphing axes stop. It's the graphing axes that are stopping the function, not the function itself. The function continues past the edge of our axes, unless in a very specific case where we're told that it stops at some place. So when we see this lack of arrows, it doesn't mean that it stops. It just means we have to remember, oh yeah, it keeps going past the edge. The only reason it stops is because it's hit this sort of boundary at the edge of it. It's not stopping because it actually stops. It's not stopping because the function stops. It's just stopping because we're looking through a window, right? If you look out through a window, if you're in your house, you're in a house and you look out through the window, you can't necessarily see everything to the left and everything to the right. You can only see what you're currently looking through in the window, right? You have to move how you're looking through the window, or move the location of the window, although that would require a sledgehammer and something no one that you live with is going to be very happy about. You could move the location of the window and be able to see different things outside, but the window fixes what you can see. That's what the graphing axes are doing to us. They're fixing what we can see in space. We're not going to use arrows in this course because we know that graphs have to keep going. We're just seeing a tiny window on a much larger function. That said, even though in this course we're not going to use arrows and we're all aware of it at this point, I want to point out there are some teachers out there and some books that will still use arrows and will still require you to use arrows. So just because I'm here saying that you probably don't need to use them, you're probably used to them by this point, doesn't mean that your teacher, if you're taking another course of the same type somewhere else, doesn't mean that that teacher is going to be okay with it. So make sure that if you have another teacher, if you have somebody else who wants you to draw arrows, make sure you do what they're telling you to do. So do what they say as long as you're in their class. For my class, you don't have to. We know what we're talking about. But in somebody else's class, they might still want you to draw arrows, so be aware of that. How do we actually graph? The easiest way to graph a function is by thinking in terms of that input to output. So remember, you put in a number and it spits out a number. So we choose a few x values and we figure out what y values get mapped to those x values, and then we plot those points. So for example, consider f of x equals x plus 1, the one we keep working with. If we plug in -2, well, that'll spit out -2 plus 1, -1. So that gets us the point -2, -1 right here. If we plug in -1, that gets us 0, so that gets us the point -1, comma 0 right here. If we plug in the point 0, then that gets us 1, 0 plus 1, so that gets the point 0, comma 1. If we plug in 1, 1 plus 1, we get 2, so we get 1, comma 2. We plug in 2, 2 plus 1, we get 3, so that gets us the point 2, comma 3. And now we've got a pretty clear idea, oh, it's just a straight line, it's just going to keep going. So at this point, we could come along and we could draw in a straight line that just keeps going through all of these points. And we know what's going on right here, right? We're able to figure out, oh, these points tell us that's what the shape of this graph is. We don't have to graph all of the points perfectly in between, because it's pretty obvious at this point that they would all just wind up being on this graph as well if we were to keep going with finer and finer steps in how often we check to see where inputs went to outputs. However, straight lines aren't necessarily the best way to connect all of our graph points together. In many ways, graphing is like playing a game of connect the dots, a mathematical game of connect the dots, but we don't necessarily want to connect with straight lines. So we usually want to connect with curves. For example, let's consider f of x equals x squared. So once again, here's a table that shows us input points, input locations going to output locations, so making points. So -3, comma 9, -2, comma 4, -1, comma 1, etc. And we can see all these points on this graph right now. But let's look what happens if we were to connect it all with straight lines. If we connect with straight lines, we get this picture right here. And while it's not a terrible representation of a parabola, it's not a very great representation of a parabola, right? A real parabola has curves going on. It curves out. It curves out as opposed to going out just in these straight, jagged lines. So we want to remember this fact. Curves are normally what's going to connect our points, not straight lines. The real f of x equals x squared is based on curves. So it looks like this picture right here. It's based on these nice, smooth curves connecting all of these points together. What about the fact that curves in one function aren't necessarily going to look exactly like the curves in the next function? That's true. But for the most part, the graphs of functions are smooth. We want to connect points to each other through smooth curves. So whenever you're drawing a graph, make sure you're connecting things smoothly without jagged, harsh connections. Each function is going to curve in different ways. Remember, the shape of a curve will be different. If we're using x squared is going to give us a totally different curve than, well, not totally different, but it'll be slightly different than x to the 4th, which is going to be different than the cube root of x. Each function that we graph will have a slightly different curve, or maybe massively different curve. But over time, you're going to become more familiar with the shapes of various functions. As you graph more and more functions, as you see more and more functions, you're going to have, oh, x squared should graph in this general way. The square root of x should graph in this general way. The, cube root of x, the x to the 5th, all these things have curves that are slightly different. It should curve a little faster, curve a little slower, those sorts of things. Your previous experience with functions helps immensely. So just pay attention and think back, when have I graphed something similar to what I'm graphing right now, and use that information to help you graph what you're working on at the moment. Finally, the idea that more points make a more accurate graph. This is an important idea. The more points you plot before drawing in your curves, the more accurate the graph becomes. Each point on the graph is a piece of information. So it makes sense that the more information we use to make our graph, the more accurate the graph is going to become. If we use more information, it will improve our graph. Let's look at a specific example. Consider f of x equals this complicated monster of a function, x cubed minus 2x squared minus 7x plus 2 all over x squared plus 1. And we'll plot it with various step sizes. What I mean is how big a jump we have between the various test points that we're setting up. So we're going from -4 to 4. So we'll start at -4 and then we'll step forward by 2. That's what I mean by a step size of 2. Don't worry, this is delta x. It means change in x. And it's just a way of saying how much we're changing x each time. So if we step forward 2, if we go from -4 here to -2 here, and then to 0 here, and then to 2 here and then to 4 here. We've stepped forward by 2 each time, and we can evaluate. I'm not putting the table down here because it's just kind of a pain for us to have to see all the numbers that we're going to be going through soon. But if we evaluated each one of these things, we get the following vertical locations, right? -2 happens to be at 0, 0 happens to be at 2, 2 happens to be somewhere between -2 and -2.5, so on and so forth. So what happens if we increase the step size, right? We don't really have a very good idea of what this thing looks like, right? It might go like this, but it could also go like this, right? It could maybe even do something crazy like this. We don't really have a good idea of what those points mean because we haven't strung enough of them together to get a very good idea. We're not used to this function, right? X cubed minus 2x squared minus 7x plus 2 over x squared plus 1. This is an unusual function. We're not used to graphing things like this, so we don't have a really good sense of what it's going to look like. So since we don't have a really good sense of what it's going to look like, we don't have any expectations, we need more points down before we're going to be able to have a good sense of where it's going. So let's consider a smaller step size of 1. So now we go -4, then -3, then -2, then -1, then 0, etc. So now we're starting to get a better idea of what the curve of the function looks like. We're starting to go, well, now we're starting to see what's happening. There's still a little confusion. We're not really quite sure what happens between -2 and 1 horizontal locations, but we're starting to get a better idea. Let's make it even smaller step size. We're at 0.5. Now it's starting to come into much clearer. We can start to understand what's going on. We go with 0.2. Now we're really starting to see what it is. We now have a great idea. Finally, we go to 0.01. Now there's so many points down that it almost makes a continuous smooth line. The only place where it isn't quite smooth is this section in the middle right here, where the function is changing so quickly that we can actually still see the space between these tiny points. But when it's not changing that fast, like, most of it here or here, we wind up seeing it strings together because we've put down so many points that it basically turns into a smooth line. And that's exactly what happens when we make a graph. We're putting down so many points that we're going, oh, that's what the smooth line is that it's making. That's what's happening when you use a graphing calculator, actually. If you use a graphing calculator, the computer inside is basically going, make a bunch of points. It's not doing the same sort of thing. It's doing tiny, tiny steps, and then it's just stringing them all together with straight lines. So it makes a whole bunch of points, and then it just strings them together, and that's what we see in the end. So the way that you graph something is you just keep using more and more points if you need more information. If you have a pretty good sense of how it's going to curve, though, you just have to put down enough points so that you can then put in the curves because you've already had the experience of working with that function before. All right, when we introduced the idea of a function, we discussed an important quality for functions. For a given input, a function cannot produce more than one output. So for example, we said that if f of 7 equals -11, then it can't also be true that f of 7 equals 20, right? Then that means that f of 7 equals two things at once. And we said that when you put something into a function, it always puts out the same output. So if we put in f of 7 the first time and it gets -11, then the second time it has to give -11, and the third time it has to give -11, and the fourth time it has to give -11. It can't ever be the case that all of a sudden things go haywire and it produces a different result. No, we can trust our function, we can trust our transformation, our process, our map, our machine, whatever analogy we want to use. We can trust the function to always give us the same output if we put in the same input. So if f of 7 equals -11, it can't be the case that f of 7 equals something else as well, something different than -11. We can turn this idea into a thing that we can see in graphs. We call this idea the vertical line test. And it says if a vertical line could intersect more than one point on a graph, it cannot be the graph of a function. So if we've got a vertical line and we bring it along like this, if we put a vertical line on anything over here on the left, it winds up not being able to intersect at more than one point, right? No matter where we bring a vertical line down on this graph on the left, it winds up passing the vertical line test. So this over here is a function. But if we do with this one over here, pretty much any point we choose, we'll wind up hitting 2 points, right? This one and this one. This one and this one. If we put it over here, it fails to hit any, but that doesn't necessarily mean it passes. If we can do it at any place on the graph, even if there's only one place on the graph where it hits the graph twice, a vertical line hits the graph twice, then that means it's not a function. So if there's a vertical line that could intersect more than one point, it is not a function. So vertical line, if it's able to intersect more than one location on the graph, it's not the graph of a function. Why? Why is this the case? Well, consider this. Every point on a graph tells us where the x value below is mapped. The points on the graph are in the form x, comma, f of x. The x that we put into the function and the f of x, the thing that the function puts out for that x. Input and output put together. So for example, let's look at this graph. This is the graph of something like a square root function. If on this graph we see at x equals 1, we get f of 1 equals 2, right? We go to 1 on the horizontal, we bring it up, and we get to 2 on the vertical, so we get that f of 1 equals 2, which is coming from the fact that the point is 1, 2. So we put in an input, and we get the output of 2. But let's consider this other one. What if we had this graph instead? On this graph, at x equals 1, we get 1, 2, and 1, negative 2. That means, since it's a graph, that means if it's the graph of a function, we've got f of 1 equals 2 and f of 1 equals negative 2. But that's not possible. A function can't spit out two different things. We can't plug in 1 and get 2 and negative 2. We plug in 1, it's not allowed to spit out two different outputs. That means we can't be looking at the graph of a function because when we plug in one number, it spits out two things, so it fails the vertical line test. This picture right here is not the graph of a function. Remember, the domain is the set of all inputs that a function can accept. We talked about this when we first talked about functions. The domain is the set of all inputs that a function can accept. It's what the domain is what the function can act on, the numbers that the function can do something to. A graph shows where a function goes, so it means that we can see the domain in the graph. Every point on the x-axis that the graph is above or below is in the domain. So every point on the x-axis that the graph is above or below has to be in the domain of that function. However, if we can draw a line on an x value and it does not cross the graph, then that x is not in the domain. So a real quick example, if we had square root of x like this, then if we try drawing a vertical line here, hey, that means that this horizontal location has to be in the domain because it winds up having an output, right? If we plug in this horizontal, it comes out as this output, so that means that it must be in the domain. But if we go over here, this horizontal location never shows up in our graph, so it must be the case that it's not included in the domain. That horizontal location is not included in the domain. So if you can draw a vertical line on an x value and it does not cross the graph, then that x is not in the domain. Remember, the domain is everything that the domain is everything that the function can take in. So if a graph is above a point, then that means it had to be able to take it in because it spits out something over that horizontal location. This is a great way to visually notice the domain, but we have to be careful to remember that our function probably continues past the edge of our viewing window. Remember the axes that we had there. So if we're going to use this idea, we have to remember that just because it seems to stop or we don't see anything past the edge of the axes doesn't mean that the domain stops there. We just need to remember that it might continue on. We have to have some sense for how it looks beyond the edge. We need to have some familiarity. We need to think, where would this keep going to? Would this keep picking up those points in its domain, or would it stop for some reason? Range is the set of all possible outputs a function can have. We also talked about this when we first introduced functions. It's all the numbers that our function could possibly produce. So domain is what can go in, range is what can come out. Like the domain, we can see the range of a function in its graph. So every point on the y-axis that the graph is left or right of is in the range. However, if you can draw a horizontal line on a y value and it does not cross the graph, then that y is not in the range. So for example, let's consider x squared. All right, so x squared looks something like this. So if we go to this horizontal location, we would be able to eventually go up and hit it, so it's in the domain. Similarly, we can go to this vertical location, and if we cut horizontally, hey, it must be some domain location that spits that out. Now, it turns out that there are actually two different domain locations that spit that out, but that's okay. Multiple domain locations, multiple inputs can give the same output, right? F of 2 squared is equal to -2 squared. That's perfectly fine. 4 and 4. So it's okay that the same input gives the same output. But the fact that there is some input that gives that output means that it must be in the range, because it can be an output. So we go to any location on our vertical axis, and if we draw a horizontal line and it cuts the graph, then that must mean that there is something that can input and give that output. So any location that is directly left or right of a vertical location means that that vertical location is in the range. That location, that number is in the range. If, on the other hand, we can draw a horizontal line on a vertical location, draw a horizontal line and it does not touch the graph, right? That would not touch x squared, then that means it's not in the range. And that makes perfect sense. Down here are the negative numbers. So can x squared spit out negative numbers? No, it can't. There's no real number that we can plug in that will spit out a negative number. So since there's no number that we can plug in to spit out a negative number, then that means we can't output negative numbers, so they can't be in the range. So the range does not include any negative numbers, which is why when we draw a horizontal line in any of these negative numbers, it's not going to touch the graph, because there's nothing that can make an output that would give a negative number. Just like with the domain, we have to be careful to remember that our function probably continues past the edge of our viewing window. That viewing window is just what we're looking through, right? So it's possible that our range is going to keep going because the graph is going to keep going. So we have to have some feeling for how the function will look past the edges of what we're able to see. So beyond the edge of our viewing window, we need to have some sense of what's going to keep going on. If we have no idea, we need to expand our viewing window so that we can have a better idea and see, oh yeah, that would keep going, or no, that actually stops. Otherwise, we won't be able to figure out exactly where the range is. Graphing calculators are really useful. If you haven't already noticed, this is a great time to point out that there's an appendix to this course that's all about graphing calculators. So if you go to the very bottom and look the appendix, there's an appendix about graphing calculators. So it might be at the end of the course, but that does not mean you should watch it last. Graphing calculators are really, really useful for doing math. And you can also use software for graphing on computers or tablets or phones. There might be just something you can download and put on a phone if you've got access to a smartphone. And you can just start doing graphs on that really quickly and easily. So graphing calculators can be extremely helpful for getting a feel in how functions work. If you're planning on taking calculus at some point, I definitely would recommend getting a graphing calculator in the near future. You're almost certainly going to want a graphing calculator for calculus, and so it won't hurt to have it now in pre-calculus. Even if you're not going to continue in math, you might find one useful for taking this course right now, and maybe for other science courses that you're currently taking or will take in the future. So if you're interested in getting a graphing calculator, and I would recommend it if you could afford it, and even if you can't afford it, there's some alternatives that I'm going to talk about that are free or extremely inexpensive. So check out the appendix on graphing calculators. We're going to talk about all about how you can use them, what they're good for, why you might want one, what are some recommendations, things to look for, that sort of stuff. So check out the appendix. There's a whole lot of information on graphing calculators there, really useful, and you're probably in a position where it's going to be useful for you to have a graphing calculator since you're taking this course, and there's a very good chance you'll go on to take calculus. So I would definitely recommend get a graphing calculator if you can afford it. So yeah, check out the appendix, lots of information there. All right, we're ready for our examples. So let's do, first we're going to graph something. Graph f of x equals x squared minus 3x plus 1. We've done this before, but let's just see a quick reminder. So we want to do this by plugging in points and getting outputs, right? So we're going to plug in x's and we'll get f of x's out. So we plug in, we're not quite sure what this looks like, right? So let's start off with a simple number that we can be pretty sure is easy to do. Let's plug in 0 first. So if we plug in 0, we get 0 squared minus 3 times 0 plus 1. So that gets us 1. If we plug in 1, then 1 squared minus 3 times 1 plus 1. Well, 1 squared is 1, minus 3 plus 1. So we've got 2 minus 3. We've got negative 1. Keep going. We plug in 2. That'll be 2 squared minus 3 times 2 plus 1. 2 squared is 4. Minus 3 times 2, that's 6. So we've got 4 minus 6 plus 1. 4 plus 1, 5. 5 minus 6. We've got negative 1 once again. Let's try going the other direction as well. So let's plug in negative 1. I'm going to just start skipping directly to the numbers because at this point we should probably be able to do this in our heads or be able to do it on paper on your own, I'm sure. So just speed things up. So negative 1 squared minus 3 times negative 1 plus 1. That'll get us positive 1. We plug in negative 2. Negative 2 squared minus 3 times negative 2 plus 1. Negative 2 squared gets us 4. Minus 3 times negative 2 gets us negative 2. Sorry. Whoops. Should be able to do it in our head. That's ironic for me to have said that. Maybe that'd be a good reason to write it out, right? So negative 1 squared minus 3 times negative 1 plus 1. So negative 1 squared, and this is also a good lesson in the fact that never just trust yourself to immediately be able to do things in your head. Negative 1 squared gets us positive 1, minus 3 times negative 1 gets us positive 3, plus 1 gets us 5. Negative 2 squared minus 3 times negative 2 plus 1. So we've got 4 plus 6 plus 1. We've got 11. And if we go forward one more, we've got at 3. We're going to see 3 squared minus 3 times 3 plus 1. We'd get 9 minus 9 plus 1. So we'd get positive 1. And one more. 4, we plug in 4, we get 4 squared minus 3 times 4 plus 1. So 4 squared, 16, minus 3 times 4, 12, plus 1. So 16 minus 12, 4, 4 plus 1, we get 5. All right, so we've got a lot of information, but there's one thing that we might notice. We might go, hey, parabolas need a bottom, right? We're graphing a squared, we're graphing a quadratic, and while we haven't formally talked about them, I'm sure you've seen parabolas quite a few times by now. We plug in 1, we get negative 1. We plug in 2, we get negative 1. We might realize, that doesn't actually give us a bottom, right? That is going to give us sort of a flat bottom. So there's probably some point in between them that's even lower. So we want to have some sense of where it's going. So let's actually plug in a number in between them. So let's plug in 1.5. If we plug in 1.5, f of 1.5, we get negative 1.25. I will spare doing that here, but we would get negative 1.25. I'll actually do it here. So if we plug in 1.5, so 1.5 squared minus 3 times 1.5 plus 1. 1.5 squared, we put that into a calculator or do it by hand. We get 2.25 minus 3 times 1.5. So we get minus 4.5 plus 1. So we've got 3.25 minus 4.5. We get negative 1.25. Great. All right, so at this point, we've actually found something that seems like it could be the bottom, and it turns out that it actually is precisely the bottom, but we don't know that technically. We haven't formally talked about it, but at least it gives us a sense of where this is going to be bottoming out. So now let's actually set up our axes, and let's plot the thing. Now, this never gets that low, right? It only gets down to negative 1.25, so let's make the bottom of our axis not that long, right? So we'll go negative 1, negative 2, because we never even reach negative 2. And we'll go up 1, 2, 3, 4, 5. And we would keep going, but we're going to top out, so we'll never actually wind up seeing the number 11 because we can't make it up that high on these axes if we're going to keep them at this reasonable thing. And let's keep it square, so the distance from the origin to a vertical 1 will be the same as the distance from the origin to a horizontal 1. So this is approximately square. I'm just roughing it by hand, but it's pretty good. 1, 2, 3, 4, negative 1, negative 2, negative 3. And I would keep going to the left, but we know that we're never going to even see that point because negative 2 is already out of where we're going to be able to plot. So let's just plot our points down. So let's see. 0 is at 1. We've got 0 at 1. So 0, 1. We've got that point. Well, let's go to the left first. So negative 1 manages to make it up to negative 5. And we're already going to be past the graph when we're going to negative 2. It's out here. We plug in 1, and we're going to be at negative 1. we plug in 2, and we're going to be at -1. Let's plug in the point in between them. 1.5 is going to be at -1.25, so it's just a little bit below. 3 is going to be at +1, and 4 is going to be at 5. So we curve this out because we know it's a parabola, so we've got some sense of how the curve looks. Right? And it would keep going on and out. Right? And it just keeps going past the edge of our axes. All right, and that's how we graph it. So this is pretty much how we can graph anything. Plot some points on a t-table, just plot some points on x and f of x, input and output. Plot the points, figure out where they're going to go, then actually put them onto the graph, set up points, and then plot them onto the graph, and then connect it with curves depending on how we know that kind of graph gets put together. All right, so this is the graph of f of x equals x cubed plus x squared minus 6x. Using it, we're going to estimate the values of f at -1.8, f at -1, f at 1, and f at 2.5. Then we're going to also estimate the values where f of x equals 0, and then finally we'll estimate the values where f of x equals -3. So first, this part right here, f at -1.8. So what we do is we just go to -1, -1.8. Well, that looks around here, so we go up. So that looks like -1.8. So we go up here, and we are about here, so looks to be a little bit above the 8, somewhere between the 8 and the 9. So if that's the case, I'd say that looks like around 8.3 to me, give or take. We're just estimating, so we don't have to be absolutely perfectly precise. But I'd say 8.5, pretty reasonable guess. 8.3, probably a little closer. So let's go with 8.3. So f of -1.8 is equal to, looks like 8.3. It's an estimate, it says estimate, it's a graph. We're never going to be able to perfectly pull information from the graph. Well, we might be able to in a few cases, but it's going to be normally something where we're getting like, we're pretty confident, but it might be slightly off by 0.01 or by 0.01, right? Well, that's the same thing. By 0.1, by lower by 0.1, these sorts of things. It's hard to be absolutely perfectly precise since we're looking at a picture, but we can get a pretty good idea. Same thing for everything else. F of -1, we just go to -1, we go up. F at -1 seems to be about this high, so I'd say probably about 5.7, 5.6, so let's say it's 5.7. F at 1, we're here, we drop down, and that one looks like it's really pretty much exactly -4, so f of 1 equals -4. F of 2.5, plug in 2.5, we go up. Pretty high. That looks like it was a pretty good vertical. Oh, hey, and look, I'd say that looks like it's pretty darn close to being right on 8, so we'll say that is 8. Great. So we've estimated the values for all of them. They might be a little bit inaccurate, but they're pretty close to right, and that's what a graph gets us. It gets us a good way to get a really good sense of what's going on. It might not be perfectly, absolutely, exactly right, but it'll get us there pretty close, which is normally enough to be able to do stuff for lots of things. Now let's look at estimating the x values for f of x equals 0. So we'll do this one in blue. Estimate the x values where f of x equals 0. So what is f of x equals 0? Well, remember, the vertical axis is f of x. That's the output. So if that's the case, then we're looking for everything that is at the 0 height, which is the same thing as the x-axis, if it's crossing the x-axis. So it looks right here, it crosses the x-axis at 2, crosses the x-axis at 0, and crosses the x-axis at -3 precisely. There's nothing else crossing there, so we can assume that we've found all the x values. So it seems that it's going to be x equals -3, 0, and 2 all cause f of x to come out as 0. Great. Finally, we'll use red for the very last one. Hopefully that won't be too confusing. Estimate the x values where f of x equals -3. So if that's the case, we go to where is f of x -3? F of x is -3, and we want to go and see, here's something. Here's something. And that's pretty close to horizontal, not perfect, I'm sorry. And there's something. So f of x equals -3 at these 3 horizontal locations. So once again, it's not absolutely, precisely, absolutely perfect, but it's pretty good. The f of x equals -3 is going to be at the x's that first one I'd say it's a little past -3, but not by much, so probably -3.2. And then the next one looks like it's around, just a little past where the, so here is +1 is right here. So this is 0.5 is right here. So I'd say that's just a hair past 0.5. So let's say it's 0.6. And then finally, here is just a little past 1.5. So I'd say it's a little bit more past it though. So probably like 1.6 or maybe 1.65. So let's go with, let's say 1.7. So maybe 1.6, maybe 1.7, but it's a little past 1.5, I can be sure of that. So that's how we use a graph to figure out things from it. We can estimate values giving an input, or we can estimate values given an output. We figure out what makes that output, or where would that input get mapped to? What would that input get output as? Great. Vertical line test, which of the below is not the graph of a function? This one's not too hard. So if these are the entirety that we're seeing, we just have to use the vertical line test. Hey, if we come along this one, we put a vertical line on this one, it's pretty easy to see that it's not going to fail it at any point, right? The vertical line is never going to cross it at anything. The only place where you might be a little curious is right here where it curves up, but it never really continues on in such a way that we can be sure, right? Any vertical line that we're making seems to cut it just once. Now, it does have this part where it sort of curves like this, but that's inaccurate. It looks like that, but the graph is actually curving a little more like this, right? And the reason why it looks like it's stacked on top of itself is because we have to have thickness to our line, right? In reality, the line is actually thinner than that. And it's even thinner than that because a point is infinitely thin. So there's no stacking because of that infinite thinness. It's only because of the thickness of our line that it winds up looking like there's something stacked. So in reality, if we come along with the vertical line test, and since a vertical line is also infinitely thin, it's not going to cut it twice because it doesn't really curve back on itself. It's only going to hit one thing at one point. So this is a function. What about this one right here? This one's really easy to see that it fails. If we cut in the middle, it's going to hit a bunch of times, right? Cuts here, here, and here, so that's more than one intersection. We go on the far sides, it will pass, but all we need is one place of failure, one place where it cut multiple times. So in the middle, it manages to fail being a function because one input manages to simultaneously have 3 outputs. So it is not a function. Finally, this one over here, same idea as the left side. Even though it looks like it's starting to get vertical, it's never actually vertical at any point. It's just, it needs to be an infinitely thin line to really understand what's going on, and our vertical line has to be infinitely thin as well. So we have to think about this beyond just going, well, it looks kind of stacked, so it must be. No, we have to go, oh, that's really only approximating where the graph is, because the line, while we can't see infinitely thin things, that's what the line is representing. So it's the case that this one is also a function because there's nothing where it clearly cuts 2 places at once. Great, that's how we use the vertical line test. Just drop vertical lines, and if there's any place where it cuts the graph more than once, where it clearly cuts the graph more than once, then it is not a function. If we can drop vertical lines everywhere and it would never cut the function more than once, then boom, it is a function. Final example, prove that there is no function that could produce a circle as its graph. So this might seem a little complicated at first. So what we want to do is we want to think, well, how could we prove this? Well, if we want to prove it, we need to show something involving circles as graphs. Well, what? Right? If we get stuck too much on trying to think, what's the right way to do this, we might never get any progress. But if we go, well, what's a circle look like? Oh, a circle. Oh, it's got stuff stacked. It would fail the vertical line test. So we know we can prove this by contradiction. So proof by contradiction, we're going to start off by assuming that there is such a thing. So proof by contradiction. Assume such a function exists, right? If there is something that could produce a circle if there is a function that could produce a circle, then look at its graph. Since it's a circle, we know what the graph of a circle looks like, right? Who knows where it's going to show up on the graph, but we know it's got to show up somewhere, right? So here's a circle, and while it's not a perfect circle, I am but a mortal, it's a good idea so we can go, oh, hey, look, just take this and cut it at any place inside of the circle. We're going to fail the vertical line test. So graph must fail vertical line test. So therefore, it is not a function. It cannot be a function. Graph cannot be a function, but it was the graph of a function. So since the graph cannot be a function, it must be that no such function exists. So our assumption was that the function did exist. So since the graph cannot be a function, but it was just the graph of a function, then there's a contradiction. The function cannot exist, so it must be that no such function exists. And we're done. That's our proof. All right, assume that what we can see on the graph below is the entirety of the function f. So in other words, there is nothing past the edge of the axes. We're looking through that window, but we've been told there's nothing interesting past the edges of the window. So this graph here is the entirety of the function f. Now we want to estimate the domain and range of f from the graph. Now remember, the domain was everything that can be input. So if we go to, say, 0, well look, hey, 0 shows up. 0 shows up in the graph. Well, what about -3? Well, -3, hey, -3 never shows up in the graph. There's nobody that it gets graphed to. Nobody gets output as. So it looks like the edge is -2. Looks like -2 is the very edge. And over here, 3 gets put in, 4 doesn't get put in, but it looks probably like 3.5 gets put in. So we'd say that the domain is going to go from -2 to 3.5. What about the range? So range is everything that can be output. So is there anything that can output at 1? Yeah. 1 manages to touch here and manages to touch here. So there is some input that spits out 1, right? If we put in an input here, we can see that it connects here. But if we go to 3 and we cut across, 3 horizontally never touches the graph, so it must be the case that there is no input that produces 3, so 3 is not in the range. The highest that we managed to get to is right here, so it looks like 1.5 is the highest that we managed to get to with the graph, right? It never shows up over here, but that's okay because it shows up somewhere. And then finally, it looks like the lowest we managed to get to is -2. So our range, the lowest location on our range is -2, and the highest location that we managed to make it to is 1.5, and we hit everything in between, right? If you go to any higher location in between, it shows up. So our range is everything in between -2 and 1.5 because all of them have something that they're able to contact. Great. All right, hope you've understood what's going on here. Hope it's like really crystallized the idea of a graph. Graphs are so important. They're going to show up in so many things in math, and they're also going to show up in science. And even if you just look in a newspaper, graphs make up a really, really big part of mathematics. So it's really important that we understand what's going on with them now because we're going to see a lot of them as we go on. All right, we'll see you at educator.com later. Bye.